Welcome, Nocturnal Minds, aboard. Your learning journey starts now. Continuing from our previous discussion on feminist perspectives in science and the role of best explanation reasoning, we now turn our attention to a fundamental question that has long captivated philosophers. What are these things called laws of nature? Mark Land kicks us off with this classic puzzle. So, Langer starts by laying out the standard view, the baseline everyone's usually working with. Think of it like sorting facts into three big boxes. First, you've got the absolute givens, the logical or metaphysical necessities. These are the bedrock truths, the kind of stuff that couldn't possibly be any other way. Like, well, triangles having three sides, try drawing a triangle with four sides, it just isn't a triangle anymore. Or the simple truth about you right now, either you're sitting or you're not. No middle ground, no alternative possibilities. Then, everything else is contingent, it could have been different. This contingent pile splits into two subcategories. On one hand, we have the gnomic necessities, the laws of nature. These are the rules the universe plays by, supposedly derived just from those laws. And on the other hand, we have accidents, regularities that happen to hold, but not because of some deep law. Think about all the coins in my pocket today, being silver-collared. That's an accident. Tomorrow, I might find a gold coin, and the regularity would break. Or consider that all solid gold cubes are smaller than a cubic mile. Also an accident, as far as the laws go. Crucially, even these laws and these accidental regularities are themselves contingent. The universe could have had different laws. Maybe magnetic monopoles exist. Maybe things can go faster than light. And it could have been an accident that gold cubes are small, or that there are no large gold cubes at all. The point is, nothing in this standard view is fixed by necessity except the purely logical stuff. Now here's where things get interesting. Look at that accidental regularity about gold cubes being small. It sounds pretty universal, doesn't it? Just like the law about U-235 cubes being small, which holds because of nuclear chain reactions. Both seem equally general, equally exceptionless within their domains. So, what makes one a law and the other just an accident? It's not obvious from the pattern itself. Plus, laws aren't always neatly labeled laws. Some fundamental principles, like the axioms of quantum mechanics or Bernoulli's principle in fluid dynamics, are treated as laws even if they aren't officially called laws. And conversely, some things we still call laws, like Newton's gravity or Bode's law for planetary orbits, might not hold up as genuine laws anymore given modern physics. It's a messy business. Philosophers also love to slice and dice laws further. Are they causal? Do they describe what happens when things interact? Or are they non-causal, like conservation laws, stating quantities stay constant? Are they fundamental, like the laws of motion, or derived from more basic principles, like Galileo's falling body law being derived from gravity, deterministic, probabilistic? Think radioactive decay probabilities, theoretical constructs versus descriptions of observable phenomena. And do they actually apply anywhere, or are some just vacuous generalizations about hypothetical scenarios that never occur? This whole landscape shows how complex the concept of a law really is. Okay, so if the standard view seems a bit shaky, some philosophers have gone further and denied the very premise that there are just these three kinds of facts. Enter the challengers. First up, the scientific essentialists, folks like Brian Ellis and John Bird. They argue that laws aren't just contingent regularities, they're metaphysically necessary. What does that mean? It means it's part of the very essence of properties like electric charge that they behave according to specific laws. You can't have electric charge without its associated causal powers and laws. It's built into the nature of the thing. Then there's Nancy Cartwright with her famous dappled world picture. She argues that nature isn't governed by neat universal laws everywhere. Instead, it's a patchwork quilt of different forces and tendencies. Some processes might just not be governed by any strict laws, and when we talk about laws, we might be talking about idealized models or describing the causal powers things possess, rather than discovering exceptionless regularities in the real world. Finally, thinkers like Ronald Geer and Bas van Fraassen push back methodologically. They say philosophy shouldn't be trying to use this abstract concept of natural law to somehow reconstruct or justify scientific practice. It's a historical idea, useful for understanding past science, but maybe not the right tool for analyzing how science actually works today. These challenges shake the foundations of the standard view. So, Len sets up the central questions he wants to tackle in this chapter. He narrows the focus to two key issues. First, an epistemological one. What practical difference does it make to how scientists reason whether they treat a statement as a law versus just an accident? Does believing something is a law change how we use it in arguments, predictions, explanations? Second, a deeper metaphysical question. What is it about the actual world that makes some statements count as laws and others merely accidental regularities? Ideally, whatever answer we give to the second question should also shed light on why the first question matters. If we can figure out the nature of laws, that should tell us how they function in reasoning. And Leng hints that if the standard view doesn't provide satisfactory answers, we might need to look for something even more radical, something beyond the usual categories. These are the big puzzles Lange aims to explore. Alright, let's dive into what laws do, starting with necessity and counterfactuals. Remember, accidents are just giant coincidences. The fact that all gold cubes are small, an accident. A large gold cube could have formed if the right conditions ever arose. But the fact that all U235 cubes are small, not an accident. Nuclear chain reactions make it physically impossible. Things must conform to the laws. This suggests a kind of necessity tied to the laws, though weaker than the absolute necessity of logic or mathematics. Now, this leads to counterfactuals, those if-only statements. Laws tell us what would have happened under different circumstances. Imagine Bill Gates wanted a giant gold cube. Even though such a cube doesn't exist, the laws governing gold and material formation suggest that if he had wanted it and the conditions allowed, there would have been one. But now, imagine Gates wanted a giant U235 cube. Even in that counterfactual scenario, the laws of nuclear physics would still kick in, and all U235 cubes would remain small. Scientists use this power of laws to reason about counterfactuals, like figuring out what Earth would be like if it orbited closer to the Sun. Accidents, however, don't support counterfactuals in the same way. Since the statement all gold cubes are small is an accident, there's some possible situation consistent with all the laws where it's false, specifically a situation where a large gold cube exists. If that situation P were true, then the accident wouldn't hold. Laws govern the counterfactual landscape, accidents don't. Moving on to explanation and confirmation. This is where the difference between laws and accidents really bites. Laws give us that feeling of had-to-ness. Take sodium salts burning yellow. Why yellow? Because it's a sodium salt, and there's a law that all sodium salts burn yellow. That law, ultimately grounded in deeper physical laws, gives the outcome a necessity. It had to burn yellow given the circumstances. Contrast that with explaining why you have 2 kids. If all families on your block have 2 kids, that's an accident. It doesn't explain why yours do. There's no irresistible force preventing childless families from moving in. This explanatory power is the core of Hempel's famous covering law model of scientific explanation. The idea that explaining something involves showing how it follows from general laws and initial conditions. Now, look at induction and confirmation. Finding silver coins in your pocket confirms. The next one will be silver. Nope. That's just coincidence. To know all coins are silver, you'd have to check them all. But a candidate law. If one sample of a substance melts at 383 Kelvin, that provides evidence, confirmation that all unexamined samples of that substance will also melt at 383 Kelvin under standard conditions. The law-like hypothesis gets confirmed inductively by its instances. This difference in how evidence supports the next case is crucial. Many philosophers argue only law-like hypotheses are confirmed inductively in this way. This distinction feels real in scientific practice, but as we'll see, pinning it down precisely is tricky. So, we've seen that laws seem to play special roles in necessity, counterfactuals, explanation, and confirmation. This strongly suggests that scientific reasoning draws a line between laws and accidents. But here's the rub. it's notoriously hard to capture exactly what that difference is. Take counterfactuals again. Consider the mathematical function relating your car's speed to how far down the gas pedal you press. That's not a law of nature, is it? It's just a feature of your specific car and engine. Yet, this function supports counterfactuals. If I had pressed the pedal halfway, the car would have gone this fast. It's invariant under certain hypothetical changes but not others, like swapping the engine. And many accidents are similarly invariant under lots of hypothetical changes. All gold cubes are small, even if I wore a red shirt instead of blue. Furthermore, past instances of your car's pedal speed function confirm future instances of that function, and it explains the car's current speed. So, even if lawhood makes a difference, it's hard to identify the precise difference it makes. Worse, if we try to define laws as the truths that hold under all nomically possible counterfactuals, we hit a circularity problem. Because nomically possible means consistent with the laws, we're defining the laws using the concept of the laws. It's like saying a bachelor is an unmarried man, and then defining unmarried man as someone who is not married to a woman. We need a better handle. So, how can we break this circularity? Lange offers a clever idea: stability. Imagine a set of truths. Let's say this set is logically closed, meaning it includes everything that logically follows from its members. Now call this set stable if every single truth G inside the set would still be true under any hypothetical counterfactual supposition P that is logically consistent with every single member of the set. Think about it. The set containing all the laws of nature and their logical consequences is going to be stable. Why? Because any counterfactual scenario that's logically consistent with all the laws is by definition a scenario where the laws still hold. So, the laws would still be true. No set containing an accident can achieve this level of stability unless it's the trivial set containing all possible truths. Why? Because you can always construct a counterfactual scenario pi that's consistent with the laws and the other accidents in the set, but inconsistent with the specific accident you're testing. For example, if your set includes the accident about gold cubes being small, you can imagine a scenario P where a large gold cube exists. This scenario is consistent with the laws, but inconsistent with the gold cube accident. So, the set of laws is maximally invariant under counterfactual perturbations. It's this maximal invariance, this stability, that gives laws their distinctive necessity. And importantly, this definition avoids the circularity because it defines stability purely based on logical consistency across potential counterfactuals, without presupposing what the laws are. Okay, so stability looks promising for distinguishing laws from mere accidents. But wait, there's another wrinkle. Stability picks out the set of nomic necessities, things that must be true given the laws. But does it distinguish the fundamental laws themselves from other truths that are merely logical consequences of those laws? Consider this. It's physically necessary that anything that is an emerald or a ruby is green or red. This is a logical consequence of the laws, assuming the law that all emeralds are green and the law that all rubies are red. But is this fact itself a law? Intuitively, probably not. It doesn't explain why a specific stone is green. To explain that, you need the fact that it's an emerald plus the law that all emeralds are green. The broader statement about emeralds or rubies being green or red is just a summary of the individual laws. This suggests that laws seem to correspond to natural kinds like emerald, ruby, sodium salt, and not every logical consequence of laws counts as a law itself. If Fodor is right about special sciences needing ceteris paribus laws, this problem becomes even more acute. It seems stability alone isn't enough to fully capture what we mean by a law. So, if stability isn't the whole story, what are laws really? Let's look at David Lewis's influential human account. Lewis takes a radically empiricist stance. He says that facts about laws supervene on the human mosaic. What's the mosaic? It's the complete set of facts about which properties are instantiated at which space-time locations, along with the geometry of space-time itself. Think of it as a detailed spatial-temporal map of everything that happens. According to Lewis, two possible worlds cannot differ in their laws unless they differ in this mosaic or its space-time structure. The properties involved in the mosaic are elite properties. They're fundamental, non-gerrymandered, categorical, no hidden modalities or propensity. Qualitate not about being a specific individual and possessed intrinsically. Objective chances also supervene on this mosaic. Now, how do we get from the mosaic to the laws? Lewis proposes the best system analysis. Imagine all possible deductive systems that describe the mosaic and the chances. These systems compete based on three criteria: informativeness, how much they tell us; simplicity, how elegant they are; and fit, how well they predict the actual history. The laws of nature are simply the contingent generalizations belonging to the single best system that wins this competition. It's a pragmatic anti-metaphysical approach. Laws emerge from the patterns in the data, favoring the simplest and most informative description. Lewis's Humean account has some real strengths. It sticks strictly to the Humean mosaic, avoiding any spooky metaphysics beyond the observable facts. It elegantly handles vacuous laws. Take Coulomb's law. It specifies the force between any two charges. But what if a specific pair of charges, say 1.234 stat coulombs and 6.789 stat coulombs, separated by exactly 1 centimeters, never actually exists? A modified law that excludes this specific pair would still be true, just like the original law. However, the original law is simpler because it doesn't have this special case. So, the best system contains the general uninstantiated Coulomb's law. But the account faces serious challenges. First, does it really supervene? Could you have two worlds with identical mosaics but different laws? Imagine a lone electron universe. Would the laws say like charges repel or like charges attract? Or would they include only one body exists? Intuitively, it seems the laws might depend on more than just the mosaic. Second, the big explanation problem. How can a mere regularity explain anything? Explaining a VFA and the regularity all F's are G feels like explaining a VFA and GA, or having distant instances explain the local one. Lewis replies that explanation is just placing the fact within the best system. Third, the counterfactual problem. Why does the best system, including all emeralds, are green, entail that another emerald would be green? Lewis says the best system influences which counterfactual word is closest. Finally, the metaphysical necessity issue. If laws are just regularities, how can they sustain counterfactuals like, if I missed my bus? Lewis argues this requires a small miracle, a violation of actual laws, to make the counterfactual scenario possible, so the laws would indeed be different. These are deep disputes between the Humean and non-Humean camps. For those interested in digging deeper into the complexities of laws of nature, Lange provides a helpful list of further reading. This includes collections like Carroll's Readings on Laws of Nature, Lewis's own final statement on his human view, Armstrong's overview of his non-human approach, influential papers by Shoemaker and Fodor on related issues like causation and special sciences, Beattie's argument about evolutionary contingency, Cartwright's elaboration of the dappled worldview, and Roberts' attempt to reconcile humanism with a governed universe. These texts offer rich explorations of the philosophical landscape surrounding laws. Now, shifting gears significantly, we move from the metaphysics of laws to a broader philosophical stance, naturalism. This section focuses on Ronald Geer's perspective on naturalizing the philosophy of science. Naturalism represents a major shift in how philosophy, especially philosophy of science, approaches its subject matter. So, what exactly is naturalism? Defining it precisely is surprisingly difficult, as Geer notes. Like many philosophical concepts, it's often defined by what it opposes: idealistic spiritualism, supernaturalism, appeals to transcendent a priori principles. But positively, naturalists insist that all aspects of the world can be accounted for naturalistically. What counts as a naturalistic account? Primarily scientific accounts, but also historical narratives or everyday explanations, as long as they don't appeal to a transcendent realm. The tricky part is defining what a scientific account is. The best naturalist answer is simply one sanctioned by currently recognized science. This avoids getting bogged down in the demarcation problem and acknowledges that scientific standards evolve. Now, a potential pitfall: doesn't claiming everything can be explained naturalistically beg the question against supernaturalism? Kierkegaard suggests a way out. characterize naturalism not as a thesis, but as a methodological stance. The stance is, for any aspect of the world, seek a naturalistic explanation before invoking the supernatural or a priori principles. This method is justified by past successes, like explaining life naturally. A key corollary: once a sufficient naturalistic explanation is found, there's no need to look for non-naturalistic ones. Once Darwin showed evolution could explain design, appeals to a designer lost their scientific relevance. This naturalistic turn in philosophy of science isn't new. Thinkers like Otto Neurath and John Dewey were pushing it early on. Nagel championed it mid-century, and Quine's famous epistemology, naturalized in 1969, was hugely influential. But the real surge of interest came in the 1980s. What fueled this? A growing dissatisfaction with the old logical empiricism, which focused heavily on conceptual analysis. The rise of the history of science, particularly Kuhn's structure of scientific revolutions, showed science as a dynamic social process, not just a logical deduction engine. And challenges from the sociology of science, which claimed to explain how science actually works. Naturalism applies to both the process of doing science and the product, scientific knowledge. The core idea is to use the same tools scientists use, or relevant fields like cognitive science or sociology, to study science. Philosophers ask questions scientists might ask, like how causality differs between quantum and classical mechanics. Resources for this naturalization include evolutionary theory, cognitive science, and the sociology of science. Jerry argues we probably need all three, and maybe more. Evolutionary theory plays a dual role in naturalizing the philosophy of science. First, it's a paradigm case of successful naturalism and provides resources. Humans evolved by natural selection. Our cognitive abilities evolved to help us survive and reproduce in our ancestral environment, not necessarily to discover abstract, universal truths. Think about it. Early humans didn't worry about the general problem of the external world. Their problems were immediate survival issues. Overestimating threats often paid off, evolutionarily. So, our evolved intuitions might not be reliable guides to truth in the way Cartesian rationalism assumes. This puts the brakes on skeptical doubts about knowing the world. But this raises a puzzle: how did creatures with these evolved, potentially biased, cognitive capacities develop such sophisticated scientific knowledge, including the theory of evolution itself? Second, evolutionary theory serves as a powerful model for understanding how scientific knowledge changes over time. Some draw a strong analogy, claiming structural isomorphism between scientific knowledge evolution and biological evolution, finding genotype-phenotype counterparts in science. Others take a looser view, noting the parallels in chance variation, selection based on utility or acceptance, and transmission of ideas. This evolutionary framing helps counterbalance rigid stage theories of science like Kuhn's, emphasizing the contingent, historical unfolding of knowledge. While an evolutionary perspective is valuable for framing scientific change, we need more specific accounts of the mechanisms driving variation, selection, and transmission in science, the genetic equivalent in the scientific ecosystem. Here, cognitive science comes to the rescue. How do scientists generate new ideas, design experiments, interpret results? Through cognitive processes like mental modeling, creating analogies, devising thought experiments, using language, making judgments and decisions. Cognitive science, specifically the cognitive study of science, aims to understand these processes. A particularly exciting development is the study of distributed cognitive systems. Traditionally, cognition was seen as computation within a brain or computer. But distributed cognition looks at cognition as spread across people, tools, and environments. Think of a complex project like the Hubble Space Telescope or a gene sequencing lab. The entire system, humans, computers, instruments, procedures, collectively produces knowledge. Whether we should still call this computation is an open question, as is whether we should attribute cognitive attributes like memory, belief, intention, or consciousness to the system as a whole. Gehr suggests keeping cognition technical and limiting attributes like belief or responsibility to human components to avoid confusion and stay closer to historical accounts of science. The big advantage, it integrates cognitive and social explanations. The social organization among humans determines how cognitive tasks are distributed throughout the entire system. Continuing with the social dimension, the sociology of science provides crucial insights for naturalizing philosophy of science. Many mechanisms of scientific change are undeniably social. Consider how scientific knowledge is transmitted. It relies on an elaborate social superstructure, education systems, mentorship, apprenticeship, publication networks. Knowledge isn't just discovered individually, it's passed down through these social channels. Even more critically, scientific knowledge isn't just individual knowledge, it's public knowledge. How does a claim become scientifically accepted? It goes through social processes like peer review and publication in reputable journals. These are not merely individual cognitive assessments, they are social certifications. If we accept the idea of a distributed cognitive system producing scientific knowledge, then this entire social infrastructure, the process of review, publication, and dissemination is part of that vast cognitive system. It's a highly distributed, socially embedded process of knowledge production and validation. One of the most common objections to naturalism, especially in ethics, is that it can't account for normativity. How can mere material processes embody norms like oughts and shoulds? Keir pushes back, arguing this objection stems from a narrow view of naturalism, equating it with crude materialism. He suggests normativity is natural. Think about human societies. Even small groups develop norms, divisions of labor, moral codes, rules for language. These arise from social interaction and history, not from some external grounding. Nietzsche's genealogy of morals shows how values are constructed, not discovered. Similarly, language norms emerge naturally. So, normativity is part of the natural world. Applying this to philosophy of science, can naturalism provide a normative basis for distinguishing good science from pseudoscience? The objection assumes there's an extra scientific essence or criterion. Naturalists deny this, pointing to the failure to find such a criterion. Instead, they propose that scientific norms are conditional. If the goal is G, use method M. The justification for these norms is empirical. M is a reliable way to achieve G. Problems arise. Specifying the goal G seems normative, and we risk a regress, needing a method to test reliability, which needs another method to test ad infinitum. Here, pragmatism offers a way out. Focus on current goals and methods, empirically test claims about reliability, adopt a stance of motivated doubt, questioning only what seems problematic, and reject the impossible task of universal Cartesian doubt. Does testing scientific models empirically require principles of inference that can't be naturalistically grounded? Geary suggests a way to frame empirical testing as a process of decision-making, not inference licensing. Let's look at a crucial experiment designed to choose between two rival models, M1 and M2. Assume the experiment has an observable output range, R. We design it so that if M1 is true, the result is very likely in range R1 and very unlikely in R2. Conversely, if M2 is true, the result is very likely in R2 and very unlikely in R1. The decision rule is straightforward. Result in R1. Choose M1, result in R2. Choose M2. The conditional norm is, if you want to empirically decide between these two models, design such an experiment. Why is this useful? Because it provides a basis for a reliable decision. If M1 is actually correct, you'll likely get R1 and choose M1. If M2 is correct, you'll likely get R2 and choose M2. Of course, there's always the possibility of inconclusive results if neither model fits well. Objections? It's comparative, and it seems subject to a regress requiring knowledge of the experimental setup's probabilities. But again, pragmatism helps. Start from current knowledge, test assumptions if seriously questioned, and recognize that comparative tests, driven by specific needs, fit the pragmatic approach of motivated inquiry. Given naturalism's rejection of a priori principles, it needs a philosophical orientation. Pragmatism provides this. The pragmatist stance relevant for naturalistic philosophy of science is clear. Start from what we currently take to be known. From there, Anything can be questioned and subjected to empirical test if there's a basis for doubt. But we don't engage in universal Cartesian doubt, questioning everything simultaneously. Instead, knowledge claims are regulated by a method of motivated doubt and empirical investigation. This pragmatist framework readily addresses objections. Do empirical tests require background empirical claims about probabilities? Yes, but those claims can themselves be tested if challenged, or they can be provisionally accepted if they're part of our current reliable knowledge base. Are comparative tests needed? Absolutely. And this aligns perfectly with pragmatism's emphasis on motivated testing driven by specific needs, like evaluating a particular rival model. Pragmatism provides the epistemological grounding for a naturalistic approach to science. How does naturalism relate to realism, the view that scientific theories aim to describe an objective reality? Often realism is contrasted with empiricism. Given naturalism's historical ties to pragmatism and empiricism, does this mean naturalists must be empiricists? Not necessarily. Geer argues naturalists should be skeptical of the idea that science has a single normative goal. Historically, scientists have pursued various aims: saving the phenomena, predicting observables, finding forces, uncovering microscopic structures, or sometimes just predicting results when realism seemed unattainable. With this diversity, naturalists are free to adopt either an empiricist or realist stance depending on the context. Importantly, the model comparison schema we discussed earlier only requires distinguishing models from data, not observable from unobservable. Data used for testing can include non-observables if they are reliably detectable. For instance, solar neutrino flux, traditionally considered non-observable, can be used as data to test models of solar fusion if we have reliable detectors. Thus, naturalism doesn't inherently commit one to anti-realism. Naturalists can certainly be realists in many contexts. Finally, let's touch on the relationship between naturalism and secularism. By definition, naturalism implies rejecting supernaturalism, and thus, the metaphysical claims of religions that posit a supernatural being. Naturalism, by relying on the methods and findings of science, actively serves the cause of secularism. How does this work in practice? Naturalism imposes constraints on claims to knowledge. First, any claim must be compatible with currently accepted scientific knowledge. Claims incompatible with relativity, like instantaneous action at a distance, are ruled out. More significantly, claims like intelligent design for evolution are ruled out because they interfere with the probabilistic independence required by evolutionary mechanisms. Second, naturalism demands testability. Claims should be testable by no reliable methods. Imagination or intuition alone isn't enough. Most metaphysical religious claims fall into this category, especially those based solely on ancient texts. This doesn't mean naturalism dictates specific ethical views. Rather, it constrains ethical debates by undercutting the appeal to divine authority or revelation as a basis for moral claims. It forces arguments to be conducted in secular terms, grounded in human experience and reason, not transcendent commandments. For those wishing to delve deeper into the rich terrain of naturalism in philosophy of science, Geer provides a comprehensive list of further reading. This includes historical perspectives like Ryder's work on American philosophical naturalism, Kitcher's review of developments, Rouse's sophisticated take on scientific practices, feminist approaches by Hankinson, Nelson, and Correny, foundational texts like Campbell's Evolutionary Epistemology and Hall's Science as a Process, Geer's own influential works, recent contributions from Churchland, Nersession, and Dagard applying cognitive science, and critical collections like DeCaro and MacArthur's volumes, Questioning and Exploring Naturalism. These resources offer diverse perspectives on this vital philosophical movement